Well, this is a discussion of Unit 6.3, the multiplication of vectors. Really straightforward, so this one will be pretty quick, but there are a couple of important applications that I'm going to leave sort of as optional for students. I don't have them assigned as specific homework questions, but I do want to show you and take the time to show you, and if you're at all interested in this type of work, um, I've recorded on the video, so that's kind of the way we're going to go about this. But the homework questions I've posted, they're going to be pretty easy and straightforward, and it's about multiplication of vectors by a scalar. So here's the lesson, and just a quick review as we've gone through these lessons. I'll post the video here in a second, and basically it just walks through a couple of examples. We're going to do a few things here, and we'll get into the Smart Notebook lesson here in a second. All right, so multiplication of a vector by a scalar. Now, a scalar is a constant, right? A constant quantity, and we can multiply our vectors by a constant quantity. This particular short section is found on page 293, and starts with a couple of properties here. Okay, so if we multiply a vector quantity by a scalar quantity, we are just enlarging or shrinking that vector. It's still going in the same direction. It creates a new vector. It's still, like I said, still going in the same direction, but we're increasing the magnitude or decreasing the magnitude depending on the value of k. So if k is positive, the vector goes in the same direction. If k is negative, it goes in the opposite direction. We can isolate our scalar quantity k. I've used this as an example here. So we can isolate that value of k, okay, and bring it out. And look like it as more of a multiplication of the vector. We'll go through a couple of examples like this, and we have a couple of following properties here. We can treat the scalar constant as sort of like the distributive property. So if we're adding two vectors together, we can apply that constant to each of the vectors. We can factor the vectors. So if we recognize that this total scalar constant might be a factor of two other numbers, we can deal with it that way. And we can do a sort of a reverse distributive property. So if we have two numbers that we're adding together, two constant numbers that we're adding together, and we're multiplying it by a vector, we can apply that sort of reverse distributive property. Think of multiplication of vectors as just magnifying or simplifying, like shrinking a vector. Okay, back in grade 9, grade 10, you guys did similar triangles, right? Similar triangles are just enlargements or shrinking property of a triangle. So if you have one triangle and you have another similar triangle, it follows the same shape, but it's larger or smaller than the original triangle here, and that's similar to when we multiply by vectors. Okay, so let's just do this really quickly. Okay, so I've got a vector v here, and I want to really quickly demonstrate what 2v looks like. Okay, so basically the idea is that I want to keep the same shape, but if I'm multiplying it by a scalar constant of 2, I'm really just doubling the vector, right? Okay, so how can I double this vector? Well, I'm going to draw the original vector here, let's say. Let's start here. Okay, there's the original vector, and I'm going to do one more, and it's just doubled. I'm going to try and do my best to draw this. If you guys are doing this, I'd use rulers. Okay, how about 3? Okay, now I'm going to do it this way. Watch, I'm going to go. Okay, so 3 just down here. So there's the first original vector. There's this 2v, and there's 3v. But in this case, since there's a negative sign on it, I'm going to... Oh. That's negative 3v. Notice that I put the arrow on the other end. And a half v. Okay, I think I've got space down here. I'm going to look to my original question. That's multiplied by a factor of a half, and that would be about there. Okay, about there, basically. So I'm going to start here and go to here. Same direction. Okay, but half the size. Okay, so that's the important factor. It doesn't change the direction, okay, unless it's negative, of course, and it just reverses the direction. But all vectors that are scalar multiples of one another are still parallel, okay, and it just changes the magnitude or the size of the vector. All right, let's go through this just by multiplication vectors. Here we've got a vector given as a string of three other vectors, 2i minus 3j plus k. I'm going to talk about I, j, and k at the end of this lesson, but vector a is defined by a linear combination of these vectors, and vector b, k, is defined by a combination of negative I plus j plus 2k. All right, so let's do a here. I'm going to just change colors, having it up a little bit. All right, a is a plus b. Okay, I've told what a is. That's 2i minus 3j plus k. It's important that I continue to use the vector symbol. I know it might be tedious to include that vector line, but please include that. So now let's collect like terms. I've got 2i minus I minus 3j plus j. Vectors are like polynomials or terms, I guess. And that's the best way to treat and understand vectors. So 2i minus I is 1i. Negative 3j plus j is negative 2j. And k plus 3k is, k plus 2k is 3k. Now, I'm going to show you one more thing here to do. Okay, that's like a 1 that we were going to talk about a little bit later, but okay, if there was a 1 here, I can write this vector as the vector 1, negative 2, and 3. We're going to talk about this more specifically at the end of this particular video lesson here. Okay, but I just want to pull that out here, that the components 1, negative 2, and 3 can be written as a vector. Okay, B. B is a little bit more challenging. I will finish it and let you guys try and do it on your own. I'll pause the video here in a second. Please work on B, and we'll compare answers here in a minute. I'm going to pick it up here. I still have some work to do, but I want to make sure that you understand and you don't go too far with this. Okay, there's the scalar factors, 2 multiplied by a, and then a minus 3 multiplied by b. I set it up this way. Then I just distribute. Okay, that's b minus 6j, and plus 6k, and plus 3. I'm going to do it, okay, with the signs, minus 3j, and then a minus 6k. You don't have to collect like terms. I will at this stage. If you guys want to save some time, you can. Just do so carefully. Okay, I always emphasize this in class. Minus 6j, minus 3j, and then a plus 6k, minus 6k. And I've got 7i minus 9j. And it looks like I've got a 0k. I don't remember. Okay, that one being, no, I don't, I think I wrote that down incorrectly here. Uh-oh. Yeah, I wrote that down incorrectly here. This should be, fix that real quick. This is a minus, okay, so that's going to be a minus, that's going to be a 2k. It's going to be a 2k, and okay, then I've got 2k here. Sorry about that. Here I cautioned you guys about making a mistake, and it was me that made the mistake. That compares to my answer. Okay. Good. Did I make another mistake with this? Oh, I'm good. Okay, so I think I've got, okay, as a point, vector point, components. Okay, I can write it like that. Again, I'll discuss that a little bit later. Okay. Unit vectors, discussion about unit vectors. A unit vector, okay, is a vector that is of length 1, okay? It's a vector, it's important. It's a way to write okay, vectors in a sort of a smaller component, but using the idea of a magnitude, we can write any given vector, we can write a vector with length 1, okay, by finding, okay, the magnitude of it and dividing, okay, dividing by, okay, the magnitude, dividing the vector by the reciprocal of the magnitude. Okay, so let's find a unit vector. Let's do this vector here as an example. If I have the vector 3, 1, -5, okay, and I want to find a unit vector. Okay, so it's going to be a vector that's going in the same direction, except it's all of length 1. So here's how I do this. I find the magnitude first. The magnitude will be, okay, 3 squared plus 1 squared plus -5 squared. Okay, so really quickly that's going to be, what, 9 and 1 is 10, 25, so it's going to be the square root of 35. Okay, so my unit vector, okay, is my vector multiplied by 1 over root 35. Okay, so that's the scalar. You're finding, okay, the 1 over the magnitude of the vector, okay, is the scalar quantity that you're multiplying it by. All right, let's do this next one here. This is a good example. Okay, I'm going to use a diagram for this, okay, and work this out. Okay, so if I've got two unit vectors x and y, okay, so that, and what I mean here, okay, is that both x and y have length 1, and they've got an angle between them of 30 degrees. Okay, let's find, okay, let's find what this looks like here. Okay, I've got to calculate the magnitude and the direction of the vector 3x minus 5y. Okay, so I'm going to set up, okay, a little diagram and use the, looks like the cosine law to find out, okay, the magnitude of this. So I've got, let's see if I can show this on a diagram here. Here's what it kind of looks like here in this diagram. Okay, so here's my original diagram, okay, for the original type of question. Okay, so there's my x and y, and I've got an angle between of 30 degrees. So my new diagram, this 3x minus y, okay, is represented in the green with the green vector here. So I've got 3x going across here, minus 5y. Okay, so those are the blue vectors. And what I've done here, okay, is use the parallelogram law to set up a new triangle, okay, that's, okay, over here. Okay, and now this is my resultant vector that I want to find. Now, a couple of things. I've got to use some basic, okay, parallel line theorem here, the 30 degrees and the 30 degrees. My new triangle, okay, has a side of 30 degrees. Eventually I'm going to have to find this triangle. That's going to be the direction of my resultant vector, and I want to find the magnitude of this. So I can use my cosine law. Okay, I've got, okay, 3x, I've got -5y, and I've got an interior angle of 30, and I can use my cosine law to find the magnitude of 3x minus 5y, and that's what I did up here. Okay, so when I expand this, okay, I'm going to put in some, okay, these are vectors. Okay, and I'm going to actually substitute in some values here. Okay, I know the magnitude, okay, is, okay, 1, talked about that, these are unit vectors. Okay, when I work all that out, that's going to be 9 plus 25, okay, minus, I think I got here a minus 15 root 3. Now that's after simplify. It was probably a minus 30 multiplied by root 3 over 2, but I've simplified that down. Okay, I've got, this is, I'm just going to carry this as my squared, so I've got this to be approximately 8, okay, 0.019, and you just can use a decimal approximation, that's fine. So my resultant vector after I take the square root is about 2.83. Now, does this seem reasonable? Seems like a small value, but remember my original vectors were unit vectors, so it's really 3, okay, and -5, okay, and that resulting value here. Okay, so that's what we've got here. All right, so now we have to find the degree measure. Now, in this case, okay, the orientation of this vector, I'm going to use the sine law. Okay, I need to find that side, and that's opposite the -5y. The sine of 30 is across from the resultant vector 3x minus 5y. If I do the sine law here, I've got, that'll be a -5 times 1, and the absolute value of that, over the sine of what I'm trying to find. Okay, this result I just found. Okay. That's the 2.83. And then the sine of 30, okay, is 25. The absolute value of -5 is 5. So if I multiply and divide, I'm left with sine. Okay, and this angle I've got in my notes here beside me, 62 degrees. Okay, and so that's the result. So my, okay, I've got 3x minus 5y vector is 2.83. Get an orientation of 66 degrees from my vector x. Okay, good. Okay, so typically in these types of questions, and again, this is more of an enrichment opportunity here, typically in these types of questions, we have to draw the original diagram in order to get some of the angles, okay, and then figure out the resultant vector here. The next one, okay, I'll do real quick. I'm going to write the answer out and just show you guys exactly what I've done here. So I'll pause this, and then we'll get into some more sort of a different answer for the unit vector discussion. I really did this quick and left lots of steps here, but here's the diagram, and I used the cosine law to find angle B here, and I've cut out some steps here. That's basically the setup of the cosine law. I did some rearranging, did some calculated work, and got B to be 104. Then I used that to get theta, which is 76 degrees. That's just a straight line property, 180 minus 104, 76 degrees. So the reason I do this, and I use that information in the beginning of the question, is in order to find those angles, because my resultant vector down here in green uses that theta. So here's my theta. Okay, so that original theta, it was over here. Okay, and I used parallel line theorem. Okay, sorry, these should have been parallel. Okay, and that's my theta now. That's what I found in my calculated in my question, and that's also down here. So that original theta angle, okay, makes up, okay, the triangle that has my resultant vector in it. So here's the resultant vector, 2u minus 3v, and the green is the resultant vector. Okay, and my theta I borrowed in here. So now I need, okay, to continue to go and actually solve my question, and I need to find the magnitude, okay, the magnitude of my green vector 2u minus 3v, and then this orientation. So I need to do, okay, these two steps here. Again, I'm going to pause my video, do the calculations, okay, and I'm going to use the cosine law and the sine law simultaneously here in order to get these values. So bear with me, and I'll be back to you in a second. Okay, a little bit of work here. So I set up my cosine law on my resultant triangle over here, okay, and worked it all out, some big numbers here, but eventually I get this expression, 16 squared plus 36 squared minus 288. That's 288 is found in here. Okay, and I get a resultant vector of 35.5 meters. Then I use the sine law to find the orientation or the direction, and that's, okay, the sine of this angle here. Cross multiply and get 78.6. So I'll just leave this here. I'll stop, and if you guys want to pause this and see this, how you did this, cosine law. Okay, and then sine law to get my two, okay, components that make up the resultant vector, that 2u minus 3v. All right. Some more questions. Okay, and the homework solutions are posted on the online class and the homework page. Okay. And real quick to unit vectors. Okay, unit vectors. This is the idea of a unit vector, and the unit vectors can be defined by the component vectors. Okay, x, y, and z along the x-axis. So I, j, and k. We were introduced to I, j, and k earlier. Okay, and I, j, and k. If they're unit vectors, you'll also see the hat symbol here, this little triangle on top of I. Okay, that just represents that it is a unit vector. So I hat is 1, 0, 0 along the x-axis. J hat is 0, 1, 0 along the y-axis. Okay, and k hat is 0, 0, 1 along the z-axis. Okay, that seems weird that they'd introduce some more variables here, I, j, and k, to represent x, y, and z, but it is what it is, and that's kind of something we need to know here. All right, so what do we need to know about these particular things? Now remember, okay, remember our original question here. Let's do this one. Okay, so let's express 2, 3, and negative 5 as a combination of unit vectors. Okay, here's how we do this. I'm just going to make sure that I've got my color here. So I've got 2, 3, and negative 5. Okay, well 2, 3, and negative 5 could be represented as the addition of three vectors. 2, 0, 0, okay, plus 0, 3, 0, plus 0, 0, negative 5. Okay, so I would add the x's up. That would be 2 plus 0 gives me 2. I would add the y's up. 0 plus 3 plus 0 gives me 3. And I would add the z components up. 0 plus negative 5 gives me negative 5. Now I can take out a scalar combination, okay, or scalar factor. Go to the first vector. I could take a factor of 2 out. Out of the second vector, I could take a factor of 3 out. And out of the third vector, I could take, okay, a negative. Let's take a negative 5 out, and it leaves me with 0, 0, 1. Okay, now we just learned that 1, 0, 0 is in fact I hat. 0, 1, 0 is j hat. And 0, 0, 1 is ijk hat. And this is similar to what I did earlier in the previous, okay, previous examples right at the beginning of this lesson. Remember I had this expression, okay, let's zoom right back here. There it is. Okay, so I had the expression of I, j, and k, and I wrote it as, okay, vector components 1, negative 2, and 3. Well, here I started, in this example, I started with the point, or the vector represented by components, and I wrote it as an expression, and that's kind of how I do that and why I do that. Okay. Okay, and here's another, again, that discussion about unit vectors. We did this previous example here. Okay, I will finish it off, but you guys should know how to do this. Now, I think I have a slightly different one. Okay, so I need magnitude of v. That's, okay, 9 plus 1 plus 25. That's square root 35. Okay, so that becomes my scalar factor here. So my unit vector, okay, v1 over root 35, then multiplied by my vector, because a unit vector goes in the same direction as the original vector, but it's just the smaller size. Okay, so if I had to confirm that and find the magnitude of that, I would, okay, expand it. Okay, and then, okay, find the, okay, actually find the magnitude of it. Okay, and I know that would be 1, because by definition, the magnitude of a unit vector is 1. Okay, so the homework questions are, okay, not really an extension of these examples. These examples are more of an optional. The lesson is more of an optional thing here. The homework questions focus on the kind of stuff we've been doing in the past. So good luck and keep at it.